All right. First of all, I have a slight correction compared to what not what's in here, but in the program it says Saber. It's supposed to be Kyber. We are not suggesting some kind of mixture between Saber and Kyber. All right, so I will start off with a very basic slide. I guess I don't really need to say too much here. Crypto right now is based on the assumption that integer factoring or the discrete logarithm is hard. I guess you all should know this if you're at this conference. Also that Peter Shor showed that these problems can be solved in polynomial time on a quantum computer. So therefore we want to base crypto on other mathematical problems. And in post-quantum crypto, we have a whole bunch of different areas. Specifically in this talk, I will focus on lattice-based crypto, and within lattice-based crypto, specifically learning with errors or rounding, and even more specifically, the module version of both of these problems. So this essentially corresponds to Kyber and Saber. So in the NIST post-quantum crypto process, we started out with a lot of schemes for encryption and signatures. And then we had a couple of rounds. At round 3, we had 9 schemes for encryption. 4 of these were finalists, and among these 3 were lattice-based. And among the lattice-based, 2 of them were Kyber and Saber. And then in round 4, Kyber was chosen for standardization. So this is essentially the motivation for why you want to study specifically Kyber and Saber. So now, Kyber and Saber, they both start by creating a CPA secure scheme, and then you add the FO transform on top to create a CCA secure scheme. So what we study in this paper is attacks on the CPA version of the scheme in the setting where the secret key is reused. Resistance against these types of attacks was considered a desirable property in the original NIST call. But you shouldn't do it like this, but somebody might still do it, so it can still be interesting to study this type of attacks. Also, more importantly, these types of attacks, they have also applications in side channel attacks and fault injection attacks. Finally, there was a paper at Asia Crypt 2021 that claimed a bound for the performance of this type of attack, and me and Qian, we thought that this bound was wrong. So we essentially wrote a paper to show that the bound was wrong. So before we continue, let's just introduce a little bit of notation. We have a function here called compress, which takes a value in ZQ and compresses it to a value in ZP, where P and Q are integers and P is smaller than Q. Then we have decompress, which goes in the other direction, going from ZP to CQ. And finally, we let B sub eta denote the central binomial distribution with parameter eta. Now, a CPA secure version of Kyber in terms of a key exchange protocol can look something like this. In the case of Saber, it will look fairly similar. I will not go into the details here, but the idea here is that Alice, using her secret key, creates a public value, sends it to Bob. Bob, using this value and his secret key, create a bunch of other values, send them over to Alice, and then Alice and Bob, they create keys, key KA and KB, and these values should of course map, and this should be the match, and these two should be their shared secret key. So now the idea for the type of attack that we study in this paper is that Eve impersonates Bob and manipulates his public parameters PB, C1, and C2. So instead of following the protocol, Eve sends sneaky values in a way such that by observing whether this leads to a match or a mismatch between the key of Alice and Eve, Eve will learn up to 1 bit of information about Alice's secret key SA. So put a little bit more simply, this allows Eve to ask a yes/no question about the contents of SA. With some restrictions on what type of yes/no questions you can ask. And then by repeatedly doing this, Eve will learn the entire secret SA. So now let's have a little bit of a more specific look at the attack, and let's specifically look at Kyber 1024. So Eve sets parameters like this. Notice that the first value here is going to be non-zero, and all the other values are 0. Now, by construction, this will lead to Alice's corresponding value M prime. It will by construction be 0 on all positions except for the one on index 0, which will mean that Alice and Bob's keys will match if and only if M prime of 0 is equal to M of 0, which is set to 1. And the value of M prime of 0 here, it simplifies to this expression here. The key thing to realize here is that we have a parameter h here and a value and the value of the secret SA on position 0. So depending on SA of 0 and h, it will either be a 1, which means a match, or a 0, which means no match. And here we have a table for how to set the parameter h depending on what you want to learn about the secret value. So in case Eve puts h equals 9, she will either learn that the secret is -2, -1, or 1, or that it's 1 or 2. And then by asking a few more questions of this type, she will learn the precise value of S of 0. So now let's have a look at this in terms of an attack. So what we have here is the probability distribution of the value of S of 0 multiplied by 16 to increase the readability a bit. So what Eve does is she makes a split here such that she either learns that the value is -2 or -1, or that it is 0, 1, or 2. Then she makes another split here. In case she learned that she was at -2 or -1, she will now learn the precise value. In case she was over here, she will either learn that the value is 0, or she will have to make a final split here to learn that the value is either 1 or 2. So this is how the mismatch attack worked in the Asia Group 21 paper, specifically on Kyber 1024. So our key concept here is to, instead of just trying to learn the contents of one position at a time, we learn about the content of multiple positions at a time. So in this talk, I will specifically show what happens when you learn about 2 positions at a time, but the idea can be generalized to more positions. And we also looked at 3 positions within our paper. So here I explain how to do it specifically for indices 0 and 128, but then you can make some minor tweaks to learn about indices I and I plus 128. And notice here that this refers to specifically the first 256 values of Kyber. Then you have a couple of different blocks, but the attack works the same way for each block. Now, slightly more concretely, Eve will set parameters like this. She will let m of 0 be 1 and or m of 128 be 1. The rest of the values of m are 0. She will let pb of 0 and 128 be some coefficient times the same value q over 32 rounded. Then she will compute C1, and she will set C2 of 0 and 128 to parameters H1 and H2, and the rest of C2 to be 0. All the exact values here doesn't really matter. What I will do now on the next couple of slides is geometric interpretation of what this allows us to do. So in one dimension, we worked with an interval, and we made different splits to step-by-step learn the contents of the secret value. Yeah, and this leads to a formula. No point in going into much details here. I will go straight to the interpretation of it. So what happens in 2 dimensions is, instead of just having an interval of values, we have a grid of different possibilities for the value of S0 and S128. And the first type of splits that we can make here is planar splits, which can be either vertical or horizontal. And this way, we would, for example, here learn that S0 is either -2, -1, or 0, or that it's 1 or 2. Here, we would learn that S128 is either 1 or 2, or 0, -1, or -2. I realize yeah, exactly. So these two, they actually don't generalize anything. This is just a 2-dimensional picture of doing something in 1 dimension. But what I will show in the next 3 slides is different types of splits that we are allowed to do now that we work in 2 dimensions. So the first thing we can do is a rectangular split, where we combine a vertical split and a horizontal split. So we make a split like this with respect to S0, a split like this with respect to S128. So the total result is that we will learn either that S0 and S128 have values within this rectangle here, or that the values are outside of this rectangle here. And this rectangle can be of any rectangular shape starting from any of the corners of this grid. Next thing we can do is a triangular split, where we will learn either that the value is within a triangle originating in any corner of the grid, or that it's outside of this triangle. So here we have one that originates in the upper right corner. Here's one that originates in the upper left corner. Finally, we can take this, combine the ideas of the previous slides and take the intersection of two triangular splits. So we have one here, and if we do a bitwise AND of all the values, we get a split where we learn either that the values of S0 and S128 are either here or, well, here. So now, next, let's have a look at what this looks like in terms of an attack, specifically on Kyber 1024. So what the values I have here are the probability distribution for the combination of values of S0 and S128, multiplied once again by a factor, this time 256, to increase the readability of the grid. So the interpretation here is, for example, that the probability that S0 is 0 while S128 is -1 is 24 divided by 256. So now let's see what type of splits this leads to in the attack that we suggested. So you start by this split here. This will teach either that the secret is in this square here, or that it's outside of this square here. Next, she makes this red split. So in case she was originally here, she makes this split. In case she was originally outside here, she makes this type of split. And then she just continues to do this step by step. And the idea is, of course, to do this in a way such that the expected number of splits is minimal. And here I have a table of the results in terms of the expected number of splits or queries. So the upper row here is the value of the AsiaCrypt 2021 paper. The one right below it is the bound that they claimed in that paper. And I call it the Huffman bound because it's connected to Huffman coding. So they showed that this is the best you could do with this type of attack, but the underlying assumption there was that you would do a mismatch attack targeting one position at a time. So we worked outside of this model and targeted multiple positions at a time, which meant that we could constructively beat the Huffman bound in all versions of Kyber and all versions of Saber. So, the ones in bold are our best results. And then I have what's called Huffman bound 2 and 3, which is Huffman bounds which is bounds for the best you could do if you could ask any type of yes/no question targeting 2 positions at a time or 3 positions at a time. Then finally, we have the Shannon bound, which is simply the entropy of the secret. So if you could ask any type of yes/no question about the contents of the secret, this is the best you could do. And we can see here that in all cases we are actually quite close to the Shannon bound. And if you compare our result with the results of AsiaCrypt 21, we have eaten up most of what's possible before you reach the Shannon bound. Now, another thing you could do is, so the attacks so far has assumed that we need to recover the full secret, but of course, you can recover parts of the secret and then solve the underlying simpler problem. So as an example here, if we take Kyber 1024 as an example, and we make around 1,500 queries, then we only need to spend around 2 to the 80 bit operations to solve for the rest of the key. And if we have around 1,700 queries, we only need around 2 to the 60 operations. And this was also studied concurrently and independently in another paper that I referenced here. Now, interesting timing here is that after we submitted our paper, but before this conference started, somebody made a huge improvement of our work. So I will say a few words on this too. What they were able to do was, instead of gaining up to 1 bit per query, they were able to gain up to p bits per query at the computational cost of 2 to the p. At the very moderate computational cost, they were able to reduce the query complexity of our paper by around 95%, which is pretty good. Interesting here is that one of the main reviewer complaints about our paper was that the result was incremental. So it was pretty nice to see that somebody took our idea, extended it, and made a huge improvement. And this attack of theirs has connections to parallel PC Oracle attacks, and here are 2 of them from this year. So for some open questions, first one of them is this improvement from the last slide, can we improve upon it further? And I believe that yes, we can. Secondly is, another question is what can be achieved on other similar lattice-based schemes, like for example, New Hope or Frodo and so on. And with that, I would like to say thank you for listening to my presentation.
We have time for a quick question.
Thanks for your talk. So I've come across a couple of papers on so-called signal leakage attacks on LWE-based key exchange. I mean, involving Nina Bindel, I think. So I was wondering, how do their signal leakage attacks relate to your attacks? Because even they use this key reusing.
I've roughly heard about those types of attacks, but I haven't really studied them, so I can't really comment on that.
Okay, thanks.
Hi, thank you for your presentation. Just a quick question about, I understand that the way the splits are done is so that it minimizes the number of expected splits. Is this, like, did you analyze the case where the adversary can, instead of, like, is limited in the number of splits and just greedily say, okay, this is, now after doing n splits, this is the most likely event, and so I can just pick this one, and not sure this is clear, but.
I'm a little confused about your...
Can you get to the matrix where you get the split? Yeah. So here, suppose you can do a single split. What if, so you're limited, you can do only a single split, and so you just have to take the most likely event. How worse it is for the adversary to do this?
So I'm still a bit confused of your question. I'm sorry, but it's, I mean, the best way of doing this is essentially an optimization problem that I did by hand in some cases and did a little bit automatic using a simple greedy approach in some other cases.
Like
The optimal way of doing this is not obvious, but also not interesting because we're so close to the Shannon bound anyways.
I understand that this is the optimal way to do. My question is, what if you get this matrix and you are only allowed to do 2 splits?
Then you would probably do it differently in case you want to learn as much as possible exactly. It depends on the setting, on exactly what you want to do.
Okay, thanks.
Okay, we have to stop here. Thank you very much again.